Hello, this is the radiation heat transfer. Review. And the radiation heat transfer depends on a number of properties that I'd like to review. One of these properties is the directional dependence. And I've drawn a diagram up here to show the directional distribution of radiation. So here we have radiation leaving a surface, and it's emitting in a lot of different directions. And you can see from this directional distribution that the most intense radiation in this particular case is normal to the surface. It doesn't have to be, but I've just drawn it here like that. And as we go away, as the angle increases, the intensity decreases. This is not necessarily true for all surfaces. It's just an arbitrary surface that I've drawn here. The amount of radiation can also depend on the wavelength of the radiation. Recall that the speed of light, which is c, equals the wavelength times the frequency. We can draw a spectral distribution which shows the dependence of emission on wavelength. Okay, so this is just an arbitrary spectral distribution right here. We have wavelength down here on the horizontal axis that may be slightly out of the picture. Here it comes. And then you can see how, it doesn't necessarily have to be a smooth curve. It depends on the surface, how well it emits at the different radiations or different wavelengths. So this is just an arbitrary curve right here. Okay, I need to talk about a few mathematical definitions before we go on. Okay, first of all, remember from calculus in plane geometry, we have what's called a plane or differential plane angle. So this would be like you were drawing on a piece of paper. And our differential angle, d alpha here, is defined as the ratio of this arc length dl right here divided by the radius. So I have d alpha, that's our differential plane angle, equals dl divided by r. Now, it's much more convenient to talk about, when we're dealing with radiation, to talk in spherical coordinates. And in spherical coordinates, we also want to define an angle called a differential solid angle. This differential solid angle is, if we have an emission or anything coming out from here, this is our, we have a cone, and at the end of the cone there's a differential area. And if we divide the differential area by the radius squared, we get what's called a solid angle. And that's defined by this differential solid angle, d omega, is defined by dan divided by r squared. Okay, so now we want to look at emission in a particular direction from an element of surface area dA1. So I've drawn the surface element dA1 over here, from which we have emission coming from that. And it can be going in all directions, but I'm just showing it coming out through one solid angle. So we have our emitted radiation. Here's our DAN. And then I've drawn an X or an X, Y, Z axis. And on the Z, I've drawn a unit vector, a normal vector from the surface. And so we can define this, we can define the radiation by this. And I've drawn another coordinate system over here to show you the spherical coordinate system. We have x, y, z, and we have a unit vector r, which is given by r, theta, and phi. Theta is measured from the z-axis in this direction. It can go from 0 all the way to pi over 2. And then phi is measured from this axis, and it can go all the way around to 2 pi. Now, it's not necessary to define this in terms of a circle right here. We could also define it in terms of a rectangle. And I've drawn that over here on the overhead. So we're going to go to the overhead now. And so over here you can see the, here's our differential. Let me zoom in on that a little bit. Okay, you can see our differential element right here. Let's look over on this one. Okay, here's our differential solid angle. We have DAN out here at the end. Our differential solid angle, remember, is defined by DAN divided by r squared. That's a little hard to see. Let me zoom a little more. Okay, if that will focus, we'll, there we go. Okay. Now, if we draw it in terms of our spherical coordinate system here, you can see that we have the rectangle that defines dAn is defined by r d theta right here and r sine theta d phi right here. So that means that dAn is going to equal r squared sine theta d phi. So that's our differential area. And if I write it out like this at the bottom, we can say that this dAn right here is equal to r d theta times r sine theta d phi, which is equal to r squared sine theta d phi. And now we can get our differential solid angle in terms of theta and phi. We just take dA and divide it by r squared, and we get our solid angle is given by sine theta d phi. Okay, so now let's go back over here and see how we're going to use that. If the surface area dA1 is opaque, then the radiation can be emitted into any direction above that surface into what's called a hypothetical hemisphere above the surface. So to get the solid angle associated with this surface, we integrate over the entire hemisphere. So we have d omega, we integrate over the hemisphere, and like I just mentioned, we're going to integrate from phi equals 0 to 2 pi, theta we integrate from 0 to pi over 2, and then this was our differential solid angle that we just defined, and from that we get that the solid angle through which the of this hemisphere is 2 pi, and we call those steer radians to indicate that they are solid angles. All right, the next thing we need to discuss is radiation intensity. And for radiation intensity, we want to consider the rate at which emission from that surface, dA1, passes through the normal surface that we talked about. So first, our definition of our definition of radiation intensity. And we'll start with the spectral intensity, which is our intensity related to wavelength. So we put the subscript lambda here to show that it's a spectral intensity, and the E stands for emitted radiation. And that's the rate at which radiant energy is emitted at wavelength lambda in the theta phi direction per unit area of the emitting surface normal to the direction, per unit solid angle about this direction, and per unit wavelength interval d lambda about lambda. Now we've said a lot there, and I think it'll make a lot more sense if we define this mathematically. So that'll be the next step. What I just said can be written as follows. So we have the radiation intensity over here, which is a function of wavelength, theta, and phi, is written as the emitted radiation divided by dA cosine theta 1 d omega d lambda. Now let me just talk about what this term right here means. This is what is actually seen. So let's go over here to the overhead. That dA cosine theta term is what is seen. Okay, so if you're looking, here's your eye, if you're looking down at the surface, you can see if you were to move up, you would be able to see more and more of the surface. As you come down, as theta increases, you can get all the way to theta equals 90 degrees. And at that point, you wouldn't be able to see the surface anymore. If you went any further than theta equals 90, you still can't see it because it's opaque. So you can go anywhere from 0 to 90 degrees. And this dA cosine theta 1 is what is seen by whatever's receiving the emission. Now, we're going to take dq d lambda, and we'll define that. We can write that as dq with the subscript lambda. So what that means is dq d lambda. And that's the rate at which radiation of wavelength lambda passes DA1, or I'm sorry, the wavelength lambda leaves DA1 and actually passes through DA1. Okay, so if we plug that in, we get this expression right here. And we could integrate this to get dq if we knew what I lambda was, but we don't. We need to get more information to get that. However, we can get the total flux, meaning the radiation per unit area emitting from the surface, by dividing by dA1. So we come over to this board, and I've defined the flux. So we divided by dA1, which meant we just get rid of that. Now, to get the total emission for a particular wavelength of our entire hemisphere, we need to integrate. So I've defined this term over here, E, for the total emission for a particular wavelength. And so we integrate again from 0 to 2 pi, theta from 0 to pi over 2. We integrate that, and that would give us the total emission for a particular wavelength. Now, when we say the total emission, what we really mean is it's really a flux. You can see that it's a flux when we say total emission, but we refer to it as the total emission. Okay, now if we want to get all the emissive power over all the wavelengths, we have to take that expression and integrate over all the possible wavelengths. And the wavelengths can run anywhere from 0 to infinity. So we plug that in here, and then we take our expression and put it in here, and that gives us the total emission over all the wavelengths. So instead of just for one particular wavelength, it's all of them. And most of the time, we're interested in the total emission over all wavelengths. Okay, so we still have to know what I is here. We don't know what that is. We can integrate this, but before we do that, we have to know how the intensity varies with lambda, theta, and phi. All right? In the next step, we're going to talk about what's called a diffuse emitter. A diffuse emitter is a surface for which emitted radiation is independent of the direction. So in our spectral intensity, we had not only wavelength, but we had a directional dependence. Well, if we call it a diffuse emitter, which is frequently the case, we can get rid of that directional dependence, and we can just say that the spectral intensity is a function only of the wavelength. So then we can find the total spectral emission. That means that the I can come out of the integral, and so then we can integrate this, and we get, for a hemisphere, we get pi. So it'd be pi times the intensity, and if we want to get the total emission over all wavelengths, we can plug it in down here, plug it in, and we integrate across that, and we get the total emission over all wavelengths for a diffuse emitter is equal to pi times the intensity, which we still have to find out what that is, but we could get it. Okay. All right, so that takes care for now of our emitted radiation. The next thing we're going to talk about is irradiation. Irradiation is the radiation that originates from emission and reflection at other surfaces and is incident on the radiation on our surface. So remember we started with radiation from our surface that was emitting. Then we have radiation that's coming in that we call the irradiation. All right, so we're going to define our spectral intensity of the irradiation. And instead of using an E subscript, we're going to use an I subscript. So this it'll look exactly the same though. So our spectral intensity of irradiation will be defined exactly the same way. Okay, and we'll use the I, and I'll have a lambda, but subscript I. Okay, using the definition of the spectral intensity, we can get the irradiation, and we integrate the irradiation over the projected area times the unit solid angle, and we get the spectral irradiation, and then we can find the total irradiation in a similar procedure by integrating over all wavelengths, and so we get the total irradiation like that. Okay, now if If the radiation is diffuse, meaning again it's independent of direction, phi and theta, then we can say that the spectral irradiation is pi times the spectral intensity, and then we can get the total irradiation is pi times the total intensity. Okay, the next term I want to talk about is radiosity. And radiosity is the emitted and the reflected radiation from a surface. So not only do we have emitted radiation, but we're also interested in the reflected radiation. And we'll define what's called the spectral radiosity by taking the spectral intensity, and we'll integrate over the solid angle and the projected angle, and we get what's called the spectral radiosity. And then we can get the total radiosity by integrating over all wavelengths, and we get, so we put that in there, and we get J. Now, we still don't know what, one thing, well, let's continue over here. If it's diffuse, and it frequently is, okay, if the, we can integrate, we can bring J outside the integral, and we can get the spectral in radiosity and the total radiosity. Remember, radiosity is based on the total area, whereas intensity was based on a projected area. But the problem with all of these things we've done so far is we never got the intensity. We need to still get I, otherwise we don't have anything. So we need to find I. So that's what we're going to do in the next step. And we're going to introduce the concept of a black body so that we can get the intensity. All right, a black body, first let me go over the characteristics of a black body. Number one, a black body absorbs all incident radiation, regardless of wavelength and direction. Number two, for a prescribed temperature and wavelength, no surface can emit more than a black body. And number three, although radiation emitted by a black body is a function of wavelength and temperature, it is independent of direction, and therefore a black body is diffuse. All right, so we want to look at we want to get the intensity of a black body, and then we'll use that to get our other terms like radiosity and so forth. Okay? To do this, we're going to use what's called the Planck distribution. Planck won the Nobel Prize. He's considered the father of quantum mechanics, and he came up with the expression for the intensity of a black body. And it's this expression right here. We have, in the numerator, we have h and CO, where h is Planck's constant, CO is the speed of light in a vacuum. In the denominator, we have the wavelength. We have Planck's constant again. We have the speed of light. We have wavelength, and another term called K, which is the Boltzmann constant, and temperature. And that will give us the spectral intensity of a black body. Okay, since the black body emitter is diffuse, we can say that the spectral emission is then equal to pi times the spectral intensity, and then that's equal to a constant over lambda to the fifth, E xb times C2 over lambda t minus 1. Okay, so now we want to look at this emission as a function of temperature. So I have a graph over here I want to show you. Okay, in the graph here, we've plotted on the horizontal axis the wavelength, and then on the vertical axis we've plotted the spectral emissive power, that E lambda b that we were just talking about. And you can see that it's a function of temperature. So if we take the temperature, for example, like what we have for solar radiation, where the average surface temperature of the sun is 5,800 degrees, the emissive power starts over here where the wavelength is 0 at around, well, it's not really a 0 wavelength, but over in this region, starts at about 10 to the 3, and then it increases and it reaches a max up around 0.4 to 0.7 nanometers, or microns. That happens to correspond with the visible spectral region, and then it starts to decrease. It comes on back down. If we were to look at, say, a temperature of 300 K, it starts over here at about 200 or 2 microns and reaches its maximum intensity at about 10 microns and then starts to drop off. Okay, so it depends on the temperature of the emitter where the maximum power is, but from this we can get the total emissive power. Okay, the next topic I want to discuss is what's called band emission. It's often necessary to know the fraction of the total emission from a black body in a certain wavelength interval, and that wavelength interval is known as a band. And so for a prescribed temperature and interval, like say from 0 to lambda, we can determine this fraction by looking at the ratio of these two expressions right here. Here's our spectral emission from 0 to lambda, which would be the band that we're interested in, and then we divide that by the total spectral emission. Okay, well, we've already integrated this, and we found that was equal to sigma t to the 4th. And so we put this in the numerator. Then we do a substitution so that instead of integrating over d lambda, we're integrating over lambda t, and we go from 0 to lambda t, and we get some function of lambda t. And we can also look at this on a graph. So if we take we could look at the fraction here of the spectral emission. And I have two graphs here. Let me find the other one. Well, that's okay. All right, so we're going from, what this does is it gives us the fraction that we can calculate there for a particular lambda t. So if we take a lambda t and say lambda t times 10 to the minus 3, we find that it's 8. We can go up here and we can see that in that band that about 83% of the total emission occurs in that band. Now we can also do this. We can look at it like this. Here's our spectral emission for a particular temperature, and we can look at the wavelength, and so this shaded area over here would represent the band from 0 to lambda. Now sorry about that. Okay, so we have the radiation emission from a black body over here. We have lambda. This would be the fraction, or this would be the emission that's going from 0 to this particular wavelength. And then we could take that temperature and we could multiply it by this wavelength, and we could put it in this graph here. I don't know if you saw this before or not. I may have had it out of range here. And so let's say it came out to 8. We plug that in here, and that would give us the fraction would be about 0.8. Now, we can also do, instead of doing the integration, it's already been done for us, so we can take a table. You have this table in your book, and let me zoom in on this. Focus a little bit. We can take a particular lambda t, and we can find the fraction from, let's say lambda t turns out to be, well here, let's use the shaded one. Lambda t turns out to be 2898. We can get the fraction. That means that it says 0.25. That means about 25%, well, 25% of the black body radiation lies in the band from 0 to whatever lambda t is. And this goes all the way out to a lambda t of 100,000 on the next page. Okay, we can also find the fraction. Let's say we wanted to know the fraction between here and here, say lambda t of 1400 and 2898. Well, what we can do is we can just find that value, subtract the two, and that gives us the band from whatever that lambda t is to that one. Okay. All right. Let's stop. $11, $12, $13. Okay, next I want to talk about emission from real surfaces. A black body is an ideal emitter in that no surface can emit any more radiation than a black body at the same temperature. So therefore we're going to use a black body as a reference. And we're going to introduce a term now called emissivity. And that we're going to use that to define the relation to the actual emission to a black body. And the emissivity is a function, it's used the Greek letter epsilon. It's a function of the wavelength, the direction, and temperature. And we define that as the actual intensity divided by the intensity of a black body radiator. Now, I want to show you an overhead here. In the figure here, let's go out here a little bit. Okay, in this figure, you can see that this, for this surface, that the intensity as a result of the emissivity is stronger in some wavelengths than it is in others. And you can also see that in this figure that the emissivity, say here's the black body emissivity, here's the real surface. And so the emissivity also varies with direction. Now, for most engineering applications, it's desired to work with surface properties that represent directional averages. And in that case, we can get what's called a spectral hemispherical emissivity, which is given by this expression here. Okay, so this is the spectral hemispherical emissivity. It's given by the actual average hemispherical spectral emissive power divided by the black body hemispherical spectral emissive power. And here we're showing the emissivity for a particular wavelength. And as we showed in the figure just a second ago, the emissivity is a function of wavelength. Now, if we integrate over all wavelengths to get a total hemispherical, if we integrate over all wavelengths to get a total hemispherical emissivity, that would be the average over all possible directions and wavelengths. We take the total hemispherical power divided by the black body hemispherical power, and we get the average emissivity for the total surface. And notice, don't forget that we assumed a diffuse emitter. Okay, the next topic will be absorption, reflection, and transmission. And how we're going to relate this to what we're going to do in class. Remember, the spectral irradiation is the rate at which radiation at a wavelength lambda is incident on a surface area at the surface and is per unit wavelength interval d lambda bot lambda. Okay, the total irradiation that's coming in encompasses all the spectral contributions and is the integral of g lambda over all wavelengths. When incident radiation interacts with a surface, there are three things that can happen. It can either be absorbed, it can be transmitted, it can be reflected. And so the total irradiation, which we've drawn as a function of wavelength here, is the reflected component, the absorbed component, and the transmitted component. That's a TR right there. Now, for most of the applications we do, the transmitted component is 0, assuming that it's opaque. Now, if it's glass, this is not going to be 0. But for most surfaces that we deal with, the transmitted portion will be 0. And in that case, the irradiation will consist of the reflected component and the absorbed component. And we can define what we call absorptivity, reflectivity, and transmissivity. Absorptivity would be the amount of irradiation absorbed divided by the total irradiation. The reflectivity would be the reflected irradiation divided by the total irradiation. And the transmissivity would be the transmitted irradiation divided by the total. Okay, all of these fractions here have to add up to 1. So alpha, or absorptivity plus reflectivity plus transmissivity, have to equal 1. And if it turns out that it's opaque, then alpha plus rho equal 1. Okay, our last topic is Kirchhoff's law. And so far we've learned that no surface has precisely the properties of a black body. However, we can approximate a black body with a cavity whose inner surface is at a uniform temperature. So let's go over here and look at the diagram here. So here we have a surface where the inside of the cavity, the inner walls are all at the same temperature. And we have radiation entering through a small cavity. And if the cavity is small, the radiation is likely to experience many reflections before it ever actually gets out. It may never get out. It goes through many reflections. And hence the radiation is almost entirely absorbed by the cavity, and then black body behavior is approximated. Now, from thermodynamic principles, it may then be argued that the radiation leaving the aperture depends only on the surface temperature and corresponds to black body emission. Moreover, since the radiation field in the cavity, which is the cumulative effect of both emission and reflection from the cavity, must be of the same form of the radiation leaving the aperture, then it follows that black body radiation field must exist within the cavity. Now, if a small body is confined within this black body radiation field, the radiation experienced by this body must be diffuse, and it will be equal to emission from a black body at T's surface. Okay, so let's look at the next diagram here. Okay, so we have if we're at steady state, there has to be thermodynamic, or there has to be thermal equilibrium, and so that we can say that the temperatures of all the different bodies within the cavity must be the same. They must be a uniform temperature. And then the net rate of heat transfer to each surface must be 0 because they're emitting and absorbing at the same time. Okay, so if we take one of the little surfaces like A1 right here, and we're going to apply an energy balance to that. Now I'm going to go to the board to do that. Okay, so we apply an energy balance to the control surface about body 1. And so we have what's going in, which would be the absorptivity times the irradiation times the area of 1 minus the emission from 1 times the area 1, it has to equal 0. Okay, well, because it's a black body, then the irradiation has to be the same as a black body radiator. So we can plug that in. Now we can divide out by A1, and we find that the emission divided by the absorptivity is equal to that of a black body. And I'm going to call this equation star because we're going to use that in just a minute. Now we can do this for each of the surfaces, and we find that we have E1 over alpha 1 equals E2 over alpha 2, blah, blah, dot, 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 which is equal to the black body emission. And this particular relationship is known as Kirchhoff's law. Okay, now since we know that alpha 1 has to be less than or equal to 1, and that no surface can have an emissive power exceeding that of a black body of the same form, we can write that the emission is equal to the absorptivity times that of the emission of a black body. Okay, we're going to use that in just a second here. Okay, now previously we've written several, about 10 minutes ago, we wrote that the emissivity is equal to the actual emission divided by that of a black body emitter. We're going to call that equation 2 star. And then we could write that the emission is equal to the emissivity times that of a black body. Now we're going to equate equations 1 star and 2 star. And if we do that and divide, we get that the emissivity divided by the absorptivity for each one of these is equal to 1. And so therefore we can say for each body in a black body emitter, or in a, like that, not a black body emitter, but in a cavity, we can say that the emission, or the emissivity, equals the absorptivity. Okay. And that's for any surface within the enclosure. And a lot of times you will know you might know the emissivity, and from that you can get the absorptivity using Kirchhoff's law. And there's one final topic I want to discuss in this review, and that's a gray surface. Now for many applications, well, what we've been saying all along is that the emissivity and the absorptivity are a function of wavelength. Well, with a gray, for many applications, we can assume that the emissivity and the absorptivity are independent of both direction and wavelength. It just turns out to be that way. And in that case, we have what is called a gray surface. And if we assume a gray surface, then we can say that the emissivity at any wavelength is equal to that of the emissivity at a particular wavelength. So we may be able to look up the emissivity at, say, 700 nanometers, and we can assume that the emissivity over all wavelengths is the same. And we can do the same thing for the absorptivity. So that completes our review of radiation for Chapter 12 in our heat transfer book. And you can use this as a background to move on for further work in our course. Thank you very much.